How is it physically possible to design a shield that literally blocks electric fields entirely, yet intentionally allows massive magnetic fields to pass straight through? Well, welcome to this explainer. I'm going to guide you through one of the most fascinating paradoxes in electromagnetic compatibility engineering, the science of selective shielding in transfer impedance. Let's get right into it. Now, you might be wondering, why do we even want to block an electric field, an E field, while letting the magnetic field, or H field, just pass right on by? Well, setting up this engineering mystery requires us to look at real-world hardware. Mastering this paradox is absolutely critical for designing robust equipment. Think about radio direction finders or pre-compliance EMC measurement probes. You see, most local noise sources generate a predominantly electric field. So if you're trying to measure a specific magnetic field in a super noisy environment, that electric noise, it's going to completely wash out your signal. You absolutely need a way to filter the physical waves themselves.
Take a look at these three variations of a loop antenna. By the end of this explainer, you're going to master the exact physics and the math behind that third image right there, the split shield loop. You're going to walk away with a rock-solid intuition for the mathematics of shield transfer impedance. We are going to break down exactly why breaking the shield is exactly what makes it work.
Moving right along to Section 1, zooming in, the physics of shield current.
To really understand how this selective filtering happens, we've got to transition from the macro level of the antenna itself and zoom way down into the micro level physics. We need to look past the surface, dive straight inside the shielding material, and see what those electrons are actually doing. And that brings us to the foundational metric of shielding effectiveness, transfer impedance. First proposed by Shulkinoff way back in 1934, transfer impedance is a unique property of the shield. Simply put, it relates the open circuit voltage that develops between the center conductor and the shield directly to the actual current flowing on the shield itself. It's the definitive metric for measuring how well a cable shield is actually protecting your signal.
Now, what's genuinely fascinating here is how a shield's behavior physically transforms depending on the frequency of the interference. At low frequencies, the transfer impedance is literally just equal to the DC resistance, the direct current resistance of the shield. But hit those high frequencies, typically anything above 1 MHz for your standard cables, and a phenomenon called the skin effect takes over. It's almost like magic. The skin effect forces the noise current to remain completely on the outside surface of the shield, while your signal current stays safely tucked away on the inside surface. It effectively separates those two currents entirely, eliminating any common impedance coupling.
Let's lock this concept of potential difference into your long-term memory with an analogy. Think of it as dipole clapping. You know an antenna radiates and picks up energy because an RF potential exists between two pieces of metal. Well, it's exactly like two hands clapping to make a sound. You physically need distance and movement between them, right? If you take those two pieces of metal and connect them so they're at the exact same potential, it's like wrapping duct tape super tightly around those two hands. You're forcing them together. Without a voltage difference, there's no current flow, no radiation, no signal pickup. The hands simply can no longer separate to clap.
All right, let's get to Section 2, the math, deriving transfer impedance.
We are definitely not going to gloss over the details here. To truly master electromagnetic compatibility, we have to follow the rigorous mathematical breakdown of the governing rules. So here is our core mathematical expression for transfer impedance. Z sub t equals 1 over I sub s multiplied by the derivative of V with respect to small l. Let me explain exactly what this mathematically tells us about the material. Z sub t represents the transfer impedance measured in ohms per unit length. This equation describes exactly how much unwanted voltage leaks into your inner conductor for every single amp of noise current flowing on the shield, per unit of cable length.
Let's methodically break down these variables so you can visually map every single piece of this equation to its physical, real-world meaning. Step 1. I sub s is our shield current. This is the external noise current traveling right along the outside of your shield. Step 2. V is the induced voltage. That's the open circuit voltage that tragically makes its way between your internal conductors and the shield. And step 3, small l, is just the length of the cable. Notice how I sub s is in the denominator. We're essentially looking for the ratio of leaked voltage per amp of shield current over a specific distance. And here's exactly why Z sub t is so absolutely crucial. According to the SAE ARP 1705 standard, shielding effectiveness, or S sub E, is roughly equal to 20 times the log of Z sub W divided by Z sub T. Z sub W is the incident wave impedance, and Z sub T is our transfer impedance. Check out the inverse mathematical relationship here. Z sub T is sitting right there in the denominator. This means the smaller your transfer impedance, the dramatically larger your shielding effectiveness becomes.
Moving to Section 3, walkthrough,
Calculating transfer impedance. The absolute crucial point here is knowing how to actually use this in practice. So let's set up a practical, step-by-step example problem to calculate Z sub t. Follow along with me as we substitute the variables into the formula. Imagine we've got a test setup where we induce a known high-frequency shield current, I sub s, of precisely 1 ampere. Over a cable length, small l, of 1 meter, we measure an induced open circuit voltage, V, of 0.005 volts. If we substitute these specific numbers right into our equation, Z sub t equals 1 divided by 1 amp multiplied by 0.005 volts divided by 1 meter. As you can see, the math simplifies perfectly. Our final Z sub t output is 0.005 ohms per meter. And remember, because transfer impedance is sitting down in the denominator of our shielding effectiveness logarithmic formula, this proves mathematically that if we were to drop that Z sub t down even further to, say, 0.001 ohms per meter, our shielding effectiveness would absolutely skyrocket. A smaller transfer impedance fundamentally, unequivocally guarantees a much more effective shield. Now, a quick note on full transparency here. Our source text references equation 2-12 to calculate the exact magnitude of the voltage produced in a loop by the magnetic field. To be clear, the exact formula for equation 2-12 is outside our current source scope for this specific explainer, but we do know definitively that it dictates the magnetic voltage pickup of the antenna.
Up next is Section 4, the pitfall, continuous versus split shields.
All right, this brings us to the big gotcha section. We've just established exactly how shields work mathematically, but here is the exact physical edge case and the glaring error that consistently trips up junior engineers when they're trying to design shielded magnetic loops. Think about this. If you build a loop antenna and wrap it in a standard continuous shield grounded at the base, yeah, it completely eliminates the electric field pickup. However, a continuous loop allows that shield current we just calculated to flow freely all the way around the circumference. And what happens? That shield current generates an equal and opposite external magnetic field. Tragically, this perfectly cancels out the very magnetic field you are trying to measure in the first place. So a continuous shield blocks both the E field and the H field. It defeats the purpose entirely.
But look at the physical break at the very top of the split shield. By intentionally introducing this tiny physical gap, you physically break the conductive path. Shield current simply cannot flow. It's trapped. And because no shield current flows, no opposing magnetic field is ever generated. The electric field lines, this still terminate right on the grounded shield, brilliantly eliminating E-field noise. But your precious magnetic field lines pass right through that gap, completely unaffected. That simple gap literally saves your magnetic sensitivity. Finally, Section 5, Summary and Outro. Let's lock in everything we've covered today with a rapid-fire summary of the absolute most critical takeaways for your long-term memory. Number 1, split shields separate E fields from H fields. Breaking the continuous loop prevents opposing magnetic fields from forming. Number 2, Shelkonoff's transfer impedance, Z sub t, is the fundamental metric dictating the true shielding effectiveness of your cables. And number 3, remember that inverse mathematical relationship. A lower transfer impedance equals exponentially better shielding power.
Our source text, Henry Ott's Electromagnetic Compatibility Engineering, opens with this brilliant quote from Albert Einstein. Everything should be made as simple as possible, but no simpler. I really hope this breakdown made the physics of transfer impedance simple for you without sacrificing any of the rigorous math that actually makes it work. It kind of leaves you wondering, doesn't it? If introducing a physical flaw, a literal gap, can completely transform and fix a shield's behavior, what other intentional imperfections might solve your next impossible engineering problem? Hit subscribe for more EMC and automotive communication protocol survival guides. Until next time, keep building.